In this final section of the class, we'll be looking at an application of projections to approximations. So our first setup, we're going to look at least squares approximation. And the setup is pretty simple. I have a linear system that's inconsistent. I don't have a solution. I want the next best thing. I want the closest thing to a solution there is. So assume ax equals b is inconsistent. And my goal, I want to find, I don't have a solution, so I want to find x star. It will not fit this equation as is, but I want it to be as close as possible, ax star to be as close as possible to b, so that minimizes the distance between the two. Minimizes the distance between ax star and b, and so really I want to know that it minimizes the length of the difference between the two. So one thing we learned in linear 1, we learned something about the b's for which there is a solution. It has a solution exactly if b is in the column space. So we have conditions, but we also have an idea here. This part will be in the column space, this part isn't because it's inconsistent, so I want the closest thing in the column space. And already with these words, actually let me remind you how that works since it's in your notes. Let me write A column 1, column 2, column, how many columns did I have in this? Column n. Then ax is c1, c2, cn times, let me spell out x as x1, x2, xn. What I'm going to do, so these are vectors, these are actually a number because that's just a vector. I'm going to leave the column vectors as is, so I'm going to get x1 times the whole column vector plus x2 times the whole second column vector. And so what I'm getting is a linear combination of the columns. And so ax is always in the column space. In fact, it's going to be everything in the column space, because if I could write something as a linear combination of the columns, the coefficients in front of the column vectors, that will give me my solution x. All right, perfect. All right, so that gives us a picture. The column space of A is going to be some subspace of our M. I'm going to have my B, which is not in the column space. Now, using the vectors AX, I can get anything. I can get anything in this blue plane. I can hit anything using AX. I want to come as close as possible to the one I like, to B. So what I'll do is I'll take the closest. And so this closest will be, well, it's going to be the projection. It's like the shadow. So the projection onto column of B. All right, and let me call this B prime. All right, so from the picture, so instead of looking at AX equals B, which is inconsistent, we're going to look at AX equals B prime. Since B prime is in the column space, this will have a solution, and that's going to be the one we're looking for. So the projection, column A of B. Alright, so before we have a formula and everything else, let me give names to everything. Let's say we're interested in this system. Then the AX that minimizes the distance will be the least squares approximation. So X star that minimizes the distance between AX star and B is called the least squares solution of AX equals B. I'll show you in a second where the least squares description or naming comes from. And the second, we'll have that the error vector, so the difference between B prime and B, this is called the error, so is the least squares error vector. And then the length of this vector, that's the error, so it is the least squares error. So I have the least square solution, I have the least square error vector, and I have the least square error. Now we're only going to look at this in our n, like I said over here, because we're looking at a system. So this norm is just going to be the Euclidean norm. And so it's really equal to e1 squared, where e1 is the first component, plus e2 squared plus en squared. And that's why it's called the least squares, is you look at the square of the error vector, and that error needs to be minimum. So we're looking at squares and taking the least possible size. All right, just for completion, to be complete, the error vector is on this graph. So it's ax, which is this, minus b, which is this, so minus b plus ax, it goes that way. We mainly care about the length of it, but the direction is down in this picture.